In this video lesson, we will state the characteristics of functions such as its domain and range, whether or not it's increasing and decreasing, and at which intervals, the x and y intercepts, and whether it's discrete or continuous. So what is the essential question we are looking at? That is, what characteristics of a real-world problem indicate that the situation can be modeled by a functional relationship? So we've already talked about these key features, but let's just review. The domain represents the x values or the independent variable. The range represents all of the y values of the function. The x-intercepts and the y-intercepts are where the function crosses, or the graph crosses the x-axis or the y-axis. Increasing and decreasing intervals, which we've already discussed, and the maximum and minimum values. What is the lowest point and the highest point of our graph, or the highest value within our table? Okay, so we have an example here using the pool problem that we looked at earlier this unit, where we have how many people are at the pool. It says the graph below shows the number of people at a swimming pool as a function of the number of hours since the pool opened for the day. The park is open for 10 hours. Okay, so what do we have as how is our graph labeled here? We have hours since the pool opened as H. Again, remember that's going to represent our X and our X values, and number of people at the pool, that's P of H, and this again is our Y axis. Okay, so the first question asks, does this graph represent a function, Y or Y not? Well, we know that a function, in order for a relationship to be a function, there is one X or one Y for every X value. So is that true in this situation? Well, one way we can check that, particularly with a nice graph like this, is to use our vertical line test. So I have a line here, or a line, a bar, and you notice it is vertical, it's not horizontal, right? So I'm just going to sort of pull it across the graph here, and I'm noting how many times does it hit the graph. So here, for every X, it hits it once. For the Y, again, at 4, it only hits it once here. At 6, it hits it once. At 8, it hits it once, and so on. So again, just to refresh, what would be a relationship that is not a function? Well, here, if I had something that looked like this, or even like this, and again, I test with my vertical line. At this point, it hits it 1, 2, 3 times. So that is not a function because this X value has how many Y's? 1, 2, and 3. So I'll erase that. So basically, we just determined it is a function. Does this graph represent a function? Yes, it does. And we could say for every X value, let me make this a little smaller. There is only one Y value. And we determine that by using the vertical line test. Okay. So now we're trying to write a function statement here, or rather a statement using function notation for the point 2, 20. Okay, so let's look, and what does that mean? So I am going to find 2 on my x-axis, and I'm going to go up to 20. I'm just going to put a dot here. So for every, I noticed that 2 represents hours since the pool opened. So 2 hours after the pool, or 2 hours since the pool opened rather, there are 200 people at the swimming pool. So that's basically what it means. So 2 hours, not 3, 2 hours after the pool opened, there are 200 people at the pool. And how would we write that as using function notation? Well, again, if we think of f of x, so I would put f of, what is our x here? It's 2. And what does that equal? F of x equals 200. And let me change it because it's not f of x, it is p of h. So p of 2 equals 200. Okay, and just to be clear, what is the 200 and where do we get it from? The 200 is right here. Change the color here. The 200 is here, and the 2 is here. So P of X, hours since the pool opened, gives me the number of people at the pool. All right, let's do the next one. Okay, there are 2 intervals of h where the function is increasing. So again, this is one of our key features of a function, whether or not, or to determine where our function is increasing and decreasing. So they said already there's 2 intervals where of h where the function is increasing. We want to write that using function notation. So where is it increasing? Well, get my pen here. I notice right here that it is going up from 0 to 2. Notice, or actually 0 to 3. There's a steady, pretty steady incline. And then it goes down, right? And it falls. And then again, from this point here at 5 to 8, again, I have another steady incline. So these are the 2 intervals in which is increasing. So how do we write that and using function note, using intervals or using inequalities rather? Well, okay, so we have 0 is less than, ooh, I don't want yellow, is less than or equal to, again, I know it's equal to because it's included, and this is our h, which is less than or equal to 3. That's one interval. That represents this interval here where it's increasing. And the second one starts at 5. It's less than or equal to h, which is less than or equal to 8. So again, these are my 2 intervals where it is increasing. And if we want to just do the decreasing, well, we can do that. We can just look at this separate part here. So that would be from 3 to 5. And again, now we're still using h. And it's also decreasing from 8 to 10. And all these values are included. All right, so what is the domain of the function? Well, the domain represents all of the x values within our graph. So if I look at this here, did I lose my pen? There we go. The domain will be represented by, again, we're creating a compound inequality or writing it as a compound inequality. 0 is less than or equal to h, which is less than or equal to 10. All those values are included from 0 to 10. And for the range, clear it up a little bit, we want to find our highest value, right? So it looks here, and this sort of leads us into another point of a key feature, finding the highest or the max value. So our max value here is at boom, 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 right here at 300. Now this is sort of well, let's not talk about that. But that could also be considered sort of a max value of that section of the graph. But this is the highest value. So what do we want to, how do we want to label that? Or rather, how do we want to write that as a compound inequality? We want to start, well, the lowest value is 0. And I can tell I'm looking at my y-axis. The lowest is 0. And the highest is 300. And again, now we're talking about range. So we're going to use P of H. All right, so now this is similar to what we did last week where we substituted our values. We sort of evaluate our graph for whatever x was. And so in this situation, we know that x is 3. So I'm going to find 3, which is here. I'm going to go up. Where do I find it? Boom, right here. And what value is that? Well, it looks like it's being divided by 50, counting up by 50. So that would be 250. So P of 3 is 250. So how would we write that, or what does it really mean? It means 2 hours, or here I go again, 3 hours this time, 3 hours after the pool opened. $250 people were at the pool. Okay. So now we're on the last section of this part. It says what four values for H will make the statement P of H equal to 200? Fun. So in this situation, I am going to actually use my same vertical line. I think I might make it red. Yep. But now I'm going to create it as horizontal because I want to see where, again, this is not the vertical line test. This is just simply seeing where it crosses at 200. Okay, and it sort of helped me determine that. So I notice here at when y is 200, x is 2, x is 4. Let's see, x is, that's so close to 6. We'll figure that out. And this looks like that is about right in the middle. All right, so if this is 7, this must be around 6.5. And if this is 9, this must be 9.5. Okay. So what are the four values? Well, x or h in this situation would be equal to 2. It would be equal to 4. Let's say we determined that as 6.5 and 9.5. Okay. So the last thing I want to cover here is, are there max and min values, and are there y and x-intercepts? Well, in this situation, we notice that our highest value in this graph was right here. All right, and we're looking at the h. So where is the graph highest at h? For h, it would be this 8. It would be 300. So our max here is 300. And let's write that as an ordered pair. The ordered pair would be 8, 300. The min, well, is there really a min? Yeah, I guess. The min, it's here at 0, right? It doesn't go past 0. So in this situation, you could say it's sort of hard to determine in this case, but you could say that the minimum value is 0, 0, or it also has a minimum here. And what are the y and the x-intercepts? So again, where does it cross or touch the y-axis? So, or the x-axis. So here, this would be our y-intercept, right?